Hi all, this is the MakeHaven badging video for the Gerber CNC. This tool is pretty exciting because it can cut full sheets of plywood, it can do full three-dimensional cutting, it's very fast and powerful, and at some point it's going to have automatic tool changing as well as other upgrades. So as a prerequisite to using this tool, you have to know how to use the shapeoko. And the reason for that is that the shapeoko is relatively inexpensive and relatively safe. So worst case scenario on the shapeoko, if you were to put your finger right onto the end mill, you could possibly lose your finger. And worst case for the machine, you could destroy the machine. But for the Gerber, it is much more dangerous and much more expensive. There are many pinch points here that could sever limbs and potentially kill you if you were to be standing in the way or leaning over and your head or hair were to get caught into the spindle. And it's also very easy to hurt the machine, to crash it, and it's very heavy. Each of these components weighs hundreds of pounds, and you can tell it to move very quickly and potentially destroy itself. So for that reason, we want you to be very comfortable on the shapeoko and confident on it before moving and graduating to the Gerber. So for example, on the shapeoko, you can see that plenty of the hold downs that are used for holding material have been all cut up, and that's fine for when you're learning, but you should not still be cutting up hold downs once you get on the Gerber. You should be very confident that you know exactly where the mill is going to go, that it's not going to be hitting anything, any of the fixturing that it shouldn't be, and that's why practicing on the shapeoko is a great stepping stone to getting to this tool. Some of the other safety concerns with this tool are fire. So there's a very powerful fan underneath that draws air down to hold material down to the surface. But if a fire were to ignite, that would draw oxygen right into the fire and keep it burning. So that's a big concern. And in addition to having pinch points and having a lot of weight, there's a very powerful spindle. So if any part of your body or hair or necktie or anything was to get caught in that would be very bad. It can also flame things with great power if they aren't clamped down very well. So as always, it's important to have eye protection on. There's also a buddy tool, which means that there needs to be someone in the room or making visual contact with you, and they know that they're your buddy and they're watching out for you, because until this tool has a safety fence around it, it is very easy for it to hurt you if you just unintentionally lean over the tool. Speaking of which, you may not lean into the tool when it is running. You cannot be on the table when it is running. So if you want to do some work on the table, you have to make sure to pause the machine, pause your job, turn off the spindle so that you're not at risk. You can't vacuum the machine while it's running. You need to stay clear of the machine, and that goes for anyone else. When you're running the machine, you need to make sure to make it clear to everyone else who may not be badged on the machine that they need to stay clear of it so that they aren't in harm's way. In terms of the materials that you can use, you can cut wood and foam, leather, rubber, all sorts of cool things. We ask you not to carbon fiber because it makes a pretty nasty dust, and also no metal. And the reason for that is if you've seen a metal CNC, it's entirely enclosed because it's throwing hot metal chips. Pieces of metal can go flying, broken end mills, and none of that is here. This is not enclosed. Someone could just be walking by, minding their own business, and get whacked with a piece of metal. So that's an unacceptable risk. In addition to the coolant that would be spraying and other factors that make this machine not really suitable for metal in this environment. And last, when you are running this machine, you need to stay with the machine. So you can't wander off somewhere. You need to stay with it, to keep an eye and ear on it. And if you would like to go to the bathroom, then by all means just pause it, and then you can go do that. But when it's running, you need to stay with it, and you need to have a buddy. So make sure to plan for that. In terms of the workflow for using this machine, it runs on LinuxCNC. So LinuxCNC needs to get G-code, which comes from another program, and then it uses the G-code to tell this router what to do to cut out your piece. So you can create that G-code with a number of programs. You can use VCarve, you can use Fusion 360, as well as a number of others. For today, we're going to be looking at VCarve, and the way that that works is we have the proprietary software here that can make the file, the actual G-code that this runs on. You can also download the software from vectric.com. and activate it using a software code available once you log into your MakeHaven account and go to the equipment page for the Gerber CNC. Then you can do all the designing on that software on your own computer and then put it on one of the MakeHaven computers to export the actual G-code that the LinuxCNC can run. Additionally, if you're just trying to do some lines or some basic G-code commands that you could type directly into the computer, then you can skip that workflow and just directly use this computer. In terms of doing full 3D stuff, I would recommend using Fusion or SolidWorks or some similar program. There will be other videos covering that, which you are more than welcome to watch. If you are doing more complicated designs, then you want to be designing in VCarve, you can use Illustrator, Inkscape, any other number of software that you can then import into something like VCarve and turn it into G-code using that software.
So here we have VCarve Pro, and just to show you how you would activate the software, you go to Help and then About, and you would put in your Makerspace ID here, which you get from the equipment page of the Gerber CNC once you're logged into the MakeHaven website. So we're going to create a new file, and we're going to start with a job setup. So for the job setup, we are just going to do a single-sided, though you can imagine doing a double-sided, and there are obviously more complications that come along with that we might touch a little bit on, and you should definitely explore. The job size, we'll say we have a piece of wood that's 10 inches by 10 inches by 3/4 of an inch thick. The normal piece of plywood. And what we're going to do is we're going to both cut through the material and we're going to engrave in the top of the material. And that requires two different setups. So when you want to cut all the way through the material, when you want to have your piece of plywood, you want to cut all the way through it, we zero off of the machine bed. So that means that when we touch off, we're going to tell the machine that 0 is on the spoil board of the CNC. And what that does is that means when it cuts down, it knows exactly where the bottom is and it doesn't go any farther. And it's important to do that because we don't want to cut into the surface of the CNC. When you do that, it degrades the ability of the vacuum to pull a vacuum when the surface is no longer flat. If you want to do engraving, then it's more important to know exactly where the top surface of this material is. So then you do material surface. So we'll start with our outline, and then we'll do another cut for our material surface. So that's the 0 position. In terms of the XY datum, datum is another word for origin in this case. The bottom left works for this scenario, though in other scenarios you might want to reference off the middle of your material or a different position, or you might want to offset it a little. If you wanted it to be down here, if you wanted it to be in the middle bottom of your position, then you can use an offset and push it over. So if you're flipping your piece over, that could be an example of why you'd want it in the middle, because the middle stays the same. But in this case, we'll just do 0 on the bottom left corner. Click OK. And now we have all these different tools going on the left side, and then as we go through the program, we'll move over to the right side. So on the left, that changes the things that we just set. Here are various shapes that are pretty similar to Inkscape or some similar program. This draws a texture, which is pretty cool. Text, nothing crazy, text on a curve. You can import bitmaps here, so an important thing to look at is the kind of things that you can import. So you can import vectors, and the kinds of files that it takes are all these DWGs, DXFs, EPS, AI, PDF, all of these cool things, SVGs. So you can import lots of vectors, but you can also import bitmaps and do the tracing here, though usually I think it's probably easier to do it in Inkscape or Illustrator or something like that. And then this draws a dimension onto your workpiece if you wanted that for some reason. Various transform operations for size, rotation, stuff like that, warping. Here are different select tools. So normal selection is for editing nodes, and then transforming, so scaling, rotating, stuff like that. Grouping, ungrouping, if you just want to measure something, but you don't actually want to mark it with that measurement. I've never actually used Vector Validator, but could be a useful tool. And let's see, these are some more sort of vector related tools for that might be familiar if you're used to Inkscape or Illustrator. So you can play around with these. in general, something to be aware of is that when you make an internal radius, so say we're going to have this rectangle here, the bit is a circle, so it can never get to this corner perfectly. There's always going to be a bit of a fillet in the corner. And so what that means, because that bit is circular, is you can just use the radius of the bit, but if you do that, that means that the tool has to come in, come to a stop, and then turn. So if you put a little more of a radius on it, so we say radius external, and we give it a radius of, say, 1 inch, then that means that it doesn't need to slow down quite as much. It can slow down a little bit and then get that turn without going totally nuts. So this whole piece of wood that we put on here is 10 inches by 10 inches. And how about we want to make something inside of it where we cut out a shape that is just going to be 8 inches by 8 inches. Why not? And we'll click apply. Now we have this shape that we just made. So close. I'm going to go to this select tool so that we can move it right to the middle or thereabouts. There are various align tools that you can use. So here's an align tool, so you can align it to the page or whatever else you want to align it to. These are another way of creating fillets. There are a few other options like that. Cropping bitmaps and offsets if you want to make a pattern. So recently I made a whole bunch of holes in a piece of material to hold the collets for the CNC. So I created one hole and then made an array of those. This is nesting, which is very useful. So nesting is if you have a whole bunch of pieces that you're cutting out and you want to be as efficient with your use of the plywood or other material as possible, then you select all those pieces and the nesting tool will try to compress them into your material that you give it so that you have as much material to work with as possible. Something that I neglected to mention is that the total work surface area of the Gerber is 53.5 inches in the X dimension, 97 inches long, and 5.5 inches tall. So when you're setting up your job, that's the biggest thing that you could put in there. Our piece of wood isn't that big, but that's what you could put. Okay. So now that we have this piece, and this again we are cutting through, so we're going to start with that operation. Now we are going to we can just look at our 3D view. It's just a piece of wood right now because this drawing we haven't told it to do anything with. So now what we can do is we can select it, and these are just other views that you can look at your material with. You can click through at your leisure, are actually making a toolpath. So this is sort of like CAD, computer-aided design, all of these tools. Here we're just designing. And then this is CAM, computer-aided machining, where we're actually going to be telling the tool what to do with this design that we just made. So there are a bunch of options. So we could say that this line that we made is a profile, and we want to follow that line. And this might look similar from the shapeoko when you're using easel. And just as a note, with easel, it does most of these things for you. It figures out a lot of these things for you. For example, we chose our datum to be on the surface of the spoil board. On easel, that's not an option. You always zero to the top left corner of your workpiece. Similarly, it does all the feeds and speeds. We're going to be figuring that stuff out here. And as another note, all of these different workflows, be it Fusion 360 or VCarve, their goal, or easel for that matter, are coming up with G-code to feed to the machine. And sometimes the program can't do the best job of figuring out exactly what it is that you want. So the best way to do it is sometimes to modify or to write the G-code yourself. So there are options in here where you can go into the actual code and modify it. But that obviously requires some familiarity with G-code, which is a relatively simple language that you can learn to understand the basic commands of, but you still want to develop that. So another tool here is the pocket. So that could say that this shape we made, we want to actually remove all the material in here. So it would make a little well, a little pocket in our piece of wood in this shape. We could have a drilling pattern, so you can put drill bits in the CNC and drill holes. Here it looks like this is for making threads, different types of engraving, doing an inlay. So a VCarve, the namesake of this software, is using a V-shaped bit to make sort of a classic sign looking object, which is a great use for it. Here it looks like it has a photo option, so you could take potentially a bitmap and apply this tool to it to make a different depths representing different densities or darkness of the pixels, fluting, texturing, and then we can get into some more three-dimensional tools. Though in general, I would recommend going from Fusion 360 if you want to do full 3D. So here it points to a few other things you can do, which is roughing and finishing. So roughing, and you may be familiar of this from Fusion, is when you remove the bulk of the material, use the biggest bit possible, and then the finishing pass, you just remove a very little bit of material. You might use a smaller bit and you take much smaller passes. You remove less material. And what that does is it leaves a much smoother, nicer last pass for the surface finish. Here you can have a whole bunch of tool databases, which will be particularly useful when we have the automatic tool changer. But you can also put in your own tool database here. So if you have a bunch of tools, you can put them in so that you know what tools you have to work with. And we'll preview it once we're ready. So for this, we are going to say that this is a profile. And we can just look again at this here in case we wanted to change anything. There are a few additional things here to look at. So this is more relevant to the model position. Material is more relevant if you do three-dimensional work. So let's say we wanted to make a golf ball. You could have the golf ball sitting up here in the top of your material or down here in the bottom. Obviously, a golf ball is not a great example because you can't get to the bottom of it. But let's just go with it. So you can change where it is, whether you have the gap above your model and your workpiece is underneath it or below. But since we are doing two-dimensional stuff, in this case, it doesn't really matter so much. Then we're going to have the rapid Z gap above material. So that means is our tool is going to do some cutting and then it wants to move somewhere else. And it's asking us how high above the material it should go. So this is set as a default in easel, but in this program, you get to choose what you want. So here, I'm just going to say 2 inches because I want it to just be well above the material. So Z1, this height clearance is way above. And then on a plunge, I also want it just to be 2 inches above because it feels, I know that I'll clear any clamps and not have any problems that way. Then the home start position is by default, it's going to be in this corner where that red dot is, but you could change it if you wanted to. So say, for example, when you're done cutting, you wanted the CNC router to go way away so that you can get to your workpiece, then you could say Y 4 feet or something like that just to get it away from your material. So that could be useful. All right, so we're going to click OK here, and now we're going to click on Profile, and we can go through these bits and pieces. So the start depth is 0 because our material is flat. We haven't already cut down material. And cut depth, we're going all the way through. So in this case, we are going to 0.75 inches because that's how thick our material is. And now we can choose our end mill. So here we're going to select our tool, and you can make up your own tool in here based on your material and whatnot. You can put in notes for yourself in case that's useful. And what we're going to do now is we're going to look at a little spreadsheet that'll help explain some of these parameters. So on this document, you can see some of the feeds and speeds and other relevant information. So we'll go through this quickly, but this is posted up on the wall by the Gerber CNC. And as a note at the top, that these are all just broad general recommendations. At the end of the day, the things that are important are getting the job done quickly, having the best finish, and you don't want to break the bit or hurt the machine. So the tool diameter generally dictates the general RPM that you want to be at. If it's a smaller bit, you can be all the way up at 18,000 RPM. That's the maximum for the machine. And as a note, 600 inches per minute is the fastest feed. So to clarify some of the terminology, the tool diameter is fairly straightforward. RPM is what we call the speed, which is rotations per minute, how fast the bit is spinning. If you're using a 2-inch bit, then you're going to be down at 12,000 for the same reason that you would do that on a router table or anything like that. The bigger the bit, the larger the diameter. Even though it's spinning at 12,000 RPM, at the edge of that bit, the surface speed that it's moving at is way faster. because the radius is so large. And in terms of chip load, so chip load is how much material each flute is moving with each rotation. We can just look at this table. So this is approximate tool size, what material, and it just tells us here. And determining the feed rate, which is how fast the actual machine is moving in a line. The way we calculate that is by using the RPM, which we found, the number of flutes on our end mill, multiplied by the chip load from this table. So now we're back in VCarve and we can put in that information. So the diameter is 1/4 inch. We have 2 flutes. The pass depth, so how much we're going to take off with each pass, we said we would do half of the diameter, so 1/8 of an inch, 0.125. And for the step over, 40%, so it has that already figured out for us. The spindle speed, we're going to bring up to 18,000. We would say that we want it to go at 432 is my memory, which gets us 0.012 chip load. And plunge rate, the rate at which it goes down, 10 inches per minute seems fairly reasonable. And this is called tool number 1, which is fine for this. So we will apply all those things and select this bit. And so now this pink dotted line has become our first tool pass, and it says it takes 6 passes. So you can do here is actually edit those passes. So it shows you each pass that it's going to take down through your material. So you can set the last pass thickness if you wanted to make it more of a finished pass. You can delete them, add them, whatnot. Then we can see how we want to do this cut. So whether you want to cut on the outside of the line or the inside of the line or on the line, I'm just going to say on the line. And then whether you do climb or conventional, in this case, it doesn't really make a whole lot of difference because we're just doing one pass. But in general, you can kind of go either way with climb or conventional. There are benefits to each in wood, depending on the bit that you're using, depending on the material. So do some experimentation. One easy way is to do a cut through your material, and whichever side looks better is the side that you should choose. So climb is when, if this is our spindle moving, or actually it looks like it's moving this way, then what we want to be doing, the bit is always going to be spinning clockwise. We're looking down over the top of it. So if it's spinning in this clockwise circle, then it might be easier to visualize like this. If it's going around, if it's cutting at that line, if that's where our material is, then it's trying to climb up the material. It's trying to race around all on its own. So that'd be climb. Versus conventional, it flips around because now when it's cutting like this, the cutting is actually pushing against the material. So the motion is opposing the cutting force. So each has their benefits. For now, we're just going to leave it at climb and on the line. And in terms of doing a separate last pass, we don't need that because we're cutting all the way through. So that's fine. But I do want to have tabs so it doesn't go flying out. Length. We'll just do 1/4 inch length tabs, 1/8 of an inch thick. That looks good. You can ramp into the material. We're going to be using an end mill that cuts fully on the tip of the bit. So we don't need ramps because it can plunge cut, but there are some cutters that can't cut at the tip. They can only cut at the side. And so for that, you would need to ramp into it because it can't plunge straight down. You can look at leads, order, all these other various things. And that looks good. So we're going to click calculate. Okay. So we're going to go here and edit this because it looks like under tabs, I need to click edit tabs. And we're going to say we want 6 tabs on this guy. And then placement, we're going to click add tabs. All right, so that looks pretty good. It looks like you can do more modification there. Click close, and now calculate. All right, so now we can use the left pointer to look at how this is going to cut down into the material. You can see the little tabs it's going to leave there. As it cuts down, we've left room for our clamps around the sides. You can also see where it's going to come in and where it's going to come out. So that all looks pretty good. And then something else that I'll note is that this is a high-speed spindle, which means that it only has much torque, has much twisting power at higher RPMs. So you really can't do very much under 10,000 RPMs. So bear that in mind, that the range is between 10 and 18,000 RPMs. So we're going to click on Toolpaths again. We can see this toolpath we have here. We can change the material if we wanted to. We can animate it. We could watch the bit as it goes around. Obviously, that was way sped up. You're going to slow it down a little bit. So it goes around. And now what we want to do is close this because, come on, close this. And now we can edit the toolpath, look at our tools, but what we really just want to do is save it. We're going to have the selected toolpath, and the post processor is exactly how it takes the program that we made and saves it as G-code. So you can see here, we're going to be looking at the EMC2 options. We're going to select one of the ones that has inches as an option. And then between those, we can see there's a G61 and a G64. So those are bits of G-code. And what that piece of G-code refers to is how it chooses to follow the lines. So G64 is the default, and that means that what it'll do is it's going to try to actually maintain the feed that the machine is moving at. And that means that sometimes, say when it's moving fast and it gets to a corner, it might have to change that path a little bit to maintain the feed. If it was coming to a sharp corner, it obviously would have to stop, which it wouldn't want to do. G61 says, nope, you're going to follow that exactly, even if it means you have to slow down a little bit. And then you can actually do some G-code to modify it a little more in between there. So what we're going to do is we're going to let it modify the path a little bit if it needs to in inches, so G64. And now what I'm on right now is a trial version on my own computer. So now actually what I'm going to do is I'm going to save this as a CRV file, which is a VCarve file, and move it over to one of the MakeHaven computers where I can then export the toolpath using the post processor as the G-code and bring it over to the Gerber. So what I'm going to do is I'm going to call this our outline and save it here. And then I'm going to go and we're going to make another one. So close this guy. And we're going to go back over here to our 2D view. And I'm going to make another design where we're going to engrave, and we'll just type here test because I'm super creative and all these various things. And for this one, as I mentioned earlier, when we do the material setup, we are going to zero off the material surface. So that's going to be the primary difference between cutting through the material and doing an engraving on the surface. We can leave our XY datum the same because we're maintaining that piece of material. We're not removing it. If we were, let's say we were removing all this top surface, we could preserve a chunk of this material somewhere else so that we can zero off the top. If, say, we're doing a finishing pass, so we wanted to zero a new tool, that's one way you could do it. Close, that looks good to go. And so now what we can do is go over here, and this is going to be a pocket. So instead of doing the profile, we're going to make this a pocket and start depth 0, same 0.75. We're going to use the same, well, I'll put in an 1/8 inch end mill so we can see 2 different end mills. In terms of the settings for it, I'm going to use the same principles. So we're going to go and look at the document. And according to the calculator, what we want to do is it has 2 flutes, 1/8 inch, a half of an 1/8 is a 16th, which is about that. And then the step over 40%, it's got that figured out. The spindle speed, we're going to put it back to 18,000. And inches per minute, what I calculated was 180 inches per minute. And we'll call that tool number 2 just for yucks. And then I don't know if this matters, but the machine is a large machine. So we'll apply those changes. And that probably just changes the tools that it shows us. And select. So now we have that tool selected. And then again, we're going to be using climb. We don't need to use any tabs for this. Our tabs aren't available because we're not going all the way through. In terms of the depth, I set it to 0.75, which was silly, but I'm going to set it to 0.25 because we just want it to go a little bit into the wood. We don't want to go all the way through. And we don't need to ramp again. And so we can calculate it. And as a note, I had to make sure that that was selected so it knew what to calculate it on. And you can see that it doesn't love this because that 1/8 of an inch bit can't get into there. So what I'm going to do is close that. I'm going to go back to 2D view, select this. And what I'm going to do is I'm going to change the font. And now by selecting the select tool, I can choose the text. So I can actually, I'll just click on this, which is the text that we just wrote. And I'm going to change the font from Times New Roman. And now we will close that. And what we can do is we can just click calculate again, right? I'll close this and on, it looks like we must have clicked that a bunch of times. So I'm just going to delete these. All right, so on pocket one, I'm going to right click and click recalculate. And there we go. So now it recalculated for this new path that we made. So it looks like it's much happier. And similarly, then we would go to save toolpath. But what I'm going to do is bring this over to the MakeHaven computer. Now that you've seen how to do it, save these toolpaths and then go back to the Gerber.
All right, so now that we have our files saved and we saved them to a flash drive that is labeled for the Gerber, I saved each pass, the profile as well as the pocket, in a folder with my name, which I encourage everyone else to do, to give yourself a folder. We're just going to quickly go over the anatomy of this tool so we're all on the same page about what it's called. This is the spoil board. So it will get spoiled with time, and then we can do another surface pass to smooth it, to bring it thinner and thinner until it needs to be replaced. However, it is really important that we try to not cut into the table. So these cuts are way too deep. This is what we're aiming for. I can't even feel it. And so that's what happens when you zero off of the surface of the table. It just comes down to the bottom and touches it just a hair. And so that'll help it last a long time, but that also means that here we're not going to get a good suction through the table. The air is going to escape through here, so it's going to be less effective there. Underneath is a huge vacuum fan that is sucking air literally through this MDF, medium density fiberboard, to suck our material down. These are clamp slots through the board, which we'll use later to hold our material down. These are called the rails that the gantry rides on. The gantry is this large bridge that rides over the machine. This is the x-axis. Then as it moves this way, that's called the y-axis. So this is y plus, and that's y negative. Over here we have the spindle. So the spindle is the actual router that is being controlled by the computer. This is the dust shoe that comes up and down to collect the dust that's being produced while we're cutting. This is the tool rack holding all of the tools. This is the control box with the computer inside. This controls the fan underneath that's sucking material down. This is air for the dust shoe as well as for the spindle. And this is the monitor where we're going to control it from. And then here's some useful sheets on the wall. This is the dust collection that goes up and over to our dust shoe. And when we're looking at starting up the machine, there are a few things that we're going to do. So one, we're going to grab a shop vac and we're going to vacuum this filter. This gets dusty and it's important that we have good airflow through our control box. So we will make sure to do that. I'm going to grab a rag from over here and wipe off the rails. It's important to keep these rails very clean so that it can ride nicely on them. We don't want things to get on there and get gunked up or scratch them, because then doesn't work very well. So those were the Y rails that I just cleaned, and now the X rail on the gantry, so we wipe those off. And now we're going to turn the air on. So the air should always be on when we're using this machine, and we'll turn it off when we're done. And that allows us to raise the dust shoe so we can get here. The dust shoe right now is controlled here, though in the future it will be controlled from the computer. And this is going to change, but fundamentally will remain mostly the same. We use this top button to raise the dust shoe. So now it's up, and we would use this bottom button to lower it to wherever we want. But for now, we want it up. And we're going to turn the machine on. So you do that by turning this huge switch and pushing this green button to turn on the computer. So we're going to give this computer a minute to start up. And you might have heard the thump as the motors on the axes engage. This just takes a minute to do its thing. You can also hear a hiss here. That's normal. There's just some air escaping from a gasket. And while we're here, we can look at this. What this does is this controls the clamping mechanism inside that holds the tool holders. So this is the spindle that spins. These are the tool holders, and these are called ISO 30 tool holders. So here, this piece that goes up into the spindle is ISO 30, and it holds an ER32 collet. So these things aren't terribly important for you to know unless you're planning on buying special collets or other special tool holders. But there you have it. This is just the big nut that goes on it that clamps down. We'll look at loading the tool in a minute. This is the pull stud at the top. So when you're loading a tool, you push this button and that opens up a clamp inside, and then you put the tool up into it, release the button, and it holds onto it. It pulls up on the pull stud and has a nice friction grip between the spindle and this taper. So it can hold on really tightly and spin it. And then over here is how we clamp down on the tools, which we will look at shortly. So now that the computer is started up, we're going to put in the credentials, which are written on the front of the machine, the login, MH, and the password, same as the Wi-Fi, dreams to make. Alright, so this is starting up, and I'm going to grab the vacuum to clean the filter. So now the machine is logged in, and we're going to go to this little penguin to start it up on this LinuxCNC controller. And we can just make this full screen. So one of the first things we can see is that this button, the e-stop button, is not pressed, which is good. What that means is that none of the e-stops are pressed, so we'll look at those. There's one on this end. If you push it, then it stops the motion and the spindle. And if we look here, you can see that that is now depressed. So if we tried to run it, it wouldn't let us. So we would need to make sure to go to the e-stop, turn it off. If you're over here and you see something's about to go awry, you can hit this quickly. It'll stop the program. If you see someone is getting in the way because they unwittingly are walking in the way of the machine and might get hurt, you hit this. If you see the operator is in a dangerous position or compromised position, you can hit that. There's also one on this end, and there's one at the control station. Right, so now that we're in the computer, you can see the basic interface, and in here there are a bunch of options. So we saw that the e-stop is not currently enabled. Then we can click on this button to actually send power to the machine. If we do that, it activates these controls. The first thing that we want to do is, if we zoom out, this red dotted line is the box that shows the whole machine. And right now, since we just turned the machine on, it's not homed, which means it doesn't know where it is. And on the shapeoko, you can use it without it being homed, because if you run it all the way to the side, it'll hit a limit switch and it'll stop, and it weighs so little that it doesn't really matter, it just clicks and stops.
But this, if it doesn't know where it is and you tell it to go to the end and it goes flying at the end, there's a lot of weight and it'll do some serious damage. So it's very important to home the machine very first thing you do when you start using the machine, and that will make sure that it's a little harder to crash it. So what we're going to do is first we're actually going to take this tool out, and when we do that we're going to hit the E-stop here. So I'm going to click this E-stop button. So first we're going to take this tool out, and what I'm going to do is come over here and hit this E-stop just to make sure that there's a 0% chance that the machine turns on while I'm touching the tool. And I'm going to push this button and it's going to release the tool just like this. Alright, so now the tool is out. I'm going to put it in this tool holder clamp and we're good to go there. And now we're going to home the machine and we're going to warm it up. So before we can home the machine, we're just going to hit this E-stop, twist it just so the E-stop is no longer pressed. Back over here, and we can enable the machine like that, and we can home all. So we can click home all, and it's first homing the Z axis, so it's going up, touching off there, and now it knows how far it is from the top. Now it's doing the X axis, and now it is doing the Y axis, coming down to find the axis nice and slowly, so that when it touches the limit switch at the end, it knows where it is and can back off to clear this rack of tool holders. Now, let's say that the machine had been left way back in that corner and it would take a long time for it to come all the way back down here. What you could do is jog the machine to bring it closer. And the way you do that is by using the arrow keys in combination with some of the other things up on here. So right now we can see that the jog speed is set to 25 inches per minute. So that means when I hit the up arrow key, so up is the y-axis, down is negative y-axis. So I'm going to hit up, which will move it this way. It's moving pretty slowly. And if I move to the right, that's right on the x-axis. And then page up and page down are the z-axis. So now it's coming down. And if you want it to go faster, you can hold shift. But be mindful of what you're doing here. So at this point it's been homed, so if I hit shift up, it moves more quickly that way. I'm going to hit shift to the right, and I could go shift to the left, and it knows where it is, so it would stop in time without crashing into the left side, but it still would be in a very abrupt stop. So you don't want to do that. You still want to approach the sides gently. So maybe you get close and then you approach it nice and slowly. You can adjust that speed here. So if you want it to be a little faster, a little slower, you can modify it here. So now with the arrow key, it's an in-between speed that is a little more comfortable. Then if you want to do discrete movements, what you can do is instead of having it on continuous mode, you can say, I want to move 50 thousandths of an inch with each click. So now every time I click the button, it moves by exactly one amount, one of whatever it is that I set. So that can also be pretty useful, especially when you're touching off on your workpiece. So now we want to warm up the spindle just to make sure that it is all nice and warm, so it is all the thermal expansion has taken place when we actually start cutting. So the way I'm going to do that is by going over to the MDI panel up here, and this is our individual G-code commands that we're given. So down here you can see a G-code file. So this is what every line of G-code looks like that you can look through. Here are individual commands. So what we're going to do is tell it one of the commands up here. For warm-up, we're going to do 16,000 RPM for 3 minutes. So here, S 16,000 means speed 16,000, and M3 tells it to start spinning in the clockwise direction. So I'm going to click go, and you might be able to hear it spinning up. See if I can show you. So it's been 3 minutes, so what we can do is type in M5, and that is the command to stop the spindle. So on here, we're going to click back to manual control. And we can see that this is showing some positions to us. So this yellow line is showing us where we went and where we are. We can just clear that now using this brush button. And now by putting it back in continuous mode, we can see that we can move it around and watch that line being made in the appropriate place now that it is homed. So that's convenient. What we can also do is by hitting Shift 3, which is the hash button, this key, the pound sign, it changes our coordinates up here. So I'm just going to hit it again so you can see, from being relative to our design to being relative to the home coordinates. So this is the position that I prefer it in, because we don't really care about this design. This is just a default design that they put in here as a placeholder. So really what I care about right now is where it is in the machine, but later we'll care more about where it is relative to our workpiece. Now, one last note is, let's say you do go really fast, you're holding Shift and you hit the arrow key and you go towards one axis. What can happen is you actually still manage to crash, to hit the side. And there are different kinds of crashes depending on the severity, but in some instances what will happen is you'll trigger the limit switch, which is actually a magnetic sensor in this case, and it'll stop it from moving. So what you would have to do in that case is click on Override Limits, and down here there would be an error that you would clear, and then what you can do is very carefully, because you've now overridden the limits, move it away from the axis that you crashed on. So that is a very useful tool. However, you want to make sure not to do that whenever possible. It's also possible to crash in another way, where say you hit something that you've mounted on the table and one of the motors decides, nope, I don't want to push that hard. And what that means is that you would actually have to reboot the whole machine. So you'd have to turn this box off and start it back up for it to be happy again. So that's what you do in the event of a crash. If it's something that seems weird or you're not exactly sure what's going on, then make sure to post on Slack and on the Gerber channel so that people know, and make sure to check the Gerber channel on Slack before you use the machine, because we're going to be constantly updating this machine, so you want to make sure to get those regular updates. So what we're going to do now is we're going to mount our workpiece on this surface. So I'm just going to grab this piece of plywood here and we're going to clamp it down. So I'm going to use this little rim that you might be able to see here just as an alignment method, so we know that it's totally flat on that edge. You're welcome to do it other ways if you would like. And now we're going to look at the various ways of clamping it down. And so we can go over here and look at the clamps. So this is the shared area for both bits and clamps for the shapeoko as well as the Gerber. And there are a few different styles. So the benefit to this style of clamp is that you don't need to use a pivot point on the back. It has a pivot built in. If you use something like this, then it's important to make sure, as you should know from the shapeoko, that the clamp is always at a declined angle, like that, pointing downwards as it clamps onto your material, which means you need to have something on the back side. So you could put a block underneath it, but these have that built in. Alright, so for holding this down, we're going to use these types of clamps. So there are a number of different clamping options. So, here, and it's important for these kinds of clamps to have them at least be level, preferably at a slight declined angle, but in this case they'll just level. And so like that. These go through. And then these nuts, these rhombus shaped nuts, drop in and twist through these holes. We can let it like that, and then right down on you, here. And I put this nut on upside down, so it's important that when you twist to the right, counterclockwise, the flats are exposed. So here I put this on upside down. I'm just going to flip that right side up. So now when I twist it to the right, those flats push against the side. That is pretty well clamped. And when we actually start cutting, what I'm going to do is activate the vacuum from underneath, and that'll provide a little extra suction to help pull it down to the table. It's important for your workpiece to be really rigid and stable, because if there's any movement in it, it's going to mess up your design. So I grabbed this bit, and we're going to load this bit up into a tool holder. So we'll see how that works. So I'm going to grab an empty tool holder, say this one, and this has an 1/8 inch collet in it. You can see the collet is labeled, but we want a 1/4 inch for our bit. So I'm going to loosen this so it comes out. So to remove this 1/8 inch collet, you just turn it upside down and give it a little push on the side, and it'll just pop out just like that. A little push from the front as well. I'm going to put this collet over here in our little collet holder under the plastic shield to keep the dust off of them. So that's where you can find some other sizes. And I'm going to actually take the 1/4 inch collet from here to load it in, just to show that process. So we'll take this out. Again, just pop that collet out. I'm going to clean off the dust in there. And I'm actually going to grab the air gun. Just to help blow this out to make sure it's really clean in there. And then the collet just pops right back in. So at an angle, you just boop, pop it in like that. Clean out the inside, make sure that's nice and clean. Okay. And then you're just going to lightly put this on. You don't want to tighten down on it at all, because you don't want to crush the collet when there's no tool in it. So then we put our tool in, and you want to have as little tool sticking out as you need, because it's more rigid with less tool sticking out. So that's a pretty reasonable amount. We're cutting through 3-inch or 3/4 inch plywood, so we have more than enough stick out for our purposes. So now we're going to put the tool in. So now we're going to put the tool right in here, and we can tighten down on it. Technically, it's supposed to be 100 foot-pounds of torque, which is a lot. We might have a torque gauge on here in the future, but for now, you just get it really nice and snug. Okay, and then we can take that out, and we can load this up into the tool, as you saw before. Make sure to hit the E-stop. I'm going to go in here with my finger and just clean it out in here, make sure there's no dust. Similarly on here, cleaning this off, make sure it's a really nice clean contact surface. Push that button, and now the tool is loaded up in there. And now what we can do is remove, I'm just going to take this other collet that we had, and tool holder, the ISO tool holder, ISO 30 that held the ER32 collet, and clip this back in here, and then the wrench can just live right in here. So this is one of my own bits, but these are a whole bunch of communal bits. You can also sharpen end mills on the Derex end mill sharpener in the metal shop. So feel free to do that. A lot of these carbide bits have plenty of life left in them. There are all kinds of cool bits, single, 2, 3 fluted, all kinds of different things. So feel free to use these. Then we're gonna load our program up in the computer, and we're gonna just take the flash drive and stick it in the side there. And the E-stop was activated when I put the tool in, so I'm just going to deactivate that. So now we can go here and we're going to open our file. So it's in media and then USB 0, and sometimes it doesn't show it, and the way to fix that is you just go down to the file manager, which opens up, and it shows us right here. That's the USB, it shows all the files, and now that we've told the computer that it's there, it should recognize it when we click open here. So we'll go up here, go to media, USB 0, and now it shows it to us. So hopefully you'll have a folder here with your files in it, and by all means feel free to come up with your cut files before coming in for your badging. So when you're getting badged, you can just do it directly on something you care about, or just any kind of practice piece, or you could do that with a facilitator if you'd rather. So we're going to start with a profile, which goes around the edge. Open it up, and you can see here all the paths are displayed on screen for us with all the dimensions, whatnot. But it's just got put at a random place in this box, right? This could be anywhere. But we told it that the datum, where we're going to start, is in this bottom left corner of our piece of wood. So it knows that we have this piece of wood, and the datum is in the bottom left corner. So we need to locate our workpiece so that it knows where it is in this big box. This is just a made up position right now. So the way we're going to do that is by coming over, and we want to touch off the x-axis. So somewhere here, somewhere on the y-axis. In this case, along the y-axis, we want to tell it down on this edge, and then the z-axis. So on the z-axis, we're actually going to be touching off this surface, but instead of the shapeoko where you have to do them all simultaneously, you put the bit right in this corner and then touch off all of those axes simultaneously. Here you can do each of them individually, which is better for a lot of reasons. So you can do them all simultaneously if this is a convenient point for you, but sometimes it is, sometimes it isn't. In terms of touching off the x and the y axes, I do prefer doing it on top because there's no risk of crashing. When you do it the alignment method where you're right on top, if you overshoot, it's no big deal. If you touch off on the side here, you risk going too far and then smashing your bit over, which would not be very good. Same obviously in the y-axis, but on top there's no risk of that. So here what we can do is enable the machine. So we're going to go over here, and now I'm just going to use the arrow keys to bring it over to our workpiece, and I'm going to hold shift just to make it go faster. It's similar to the water jet if you're familiar with that. And now what we can do is, it's a little more delicate because we're right around our workpieces, but we're going to do the z-axis first. So we're going to come over here. And for the z-axis, we can touch off anywhere on this piece of MDF because it's all the same height. We're going to come down, and we can do the same paper technique as we do on the shapeoko. Right over here. Down. I'm going to get close, and then I'm going to stop before we get too close. So I'm going to shift over to the increment mode, where we go by a small amount so I don't risk accidentally hitting our surface. And because of this acrylic box, sometimes it's easier to look down through the box. I'm not sure if you can see it in the camera, but that's what I'm going to be doing. So bring it down. What happened is I'd actually loaded the tool so far up in the tool holder, in the collet, that it wasn't able to reach all the way down to the table. This had bottomed out, and so it couldn't reach down any farther. So I just increased the stick out a little bit. So now we can, again, raise the dust shoe all the way up, and it'll actually be a little easier to get to it, a little, maybe more over there. So I'm just gonna move it over there, making sure not to hit anything. So now, over here on an unmarred piece of the MDF, I'll just come over here and put a piece of paper underneath there, and I'm going to come down with Z. And then when we get close, we're going to switch over to incremental. And get, say, 0.05. And now we're just going to page down and now get to 0.01, maybe even 0.005. And I'm just going to do the same thing as on the shapeoko, where you just shimmy the paper until it can't move. And then I'll go up, say 1, so I can pull this out, down 1 to go to that same height, and down 1 more because a sheet of paper is about 5/1000 of an inch thick. Alright, so now it's touching the Z0. So what we want to do is touch off that axis. So Z is selected here, and we're going to click touch off. And what we're going to do now is tell it that the Z coordinate relative to the workpiece is 0. However, let's say that we hadn't done that last click and we knew that our shim or our piece of paper was 5/1000. Then we could put that thickness of the paper in there, and so it would tell it that actually we're not touching, we're not at 0, we're at 5/1000 above 0. But we didn't do that, so we're going to put in 0. And so now our Z axis, you might have seen this move, is now touched off. So now we're going to do the other axes, and I'm going to do those up on the top surface. Because we're doing them individually, it doesn't really care where the Z is. So we're going to bring U up. I'm going to go back to continuous mode, so we're not moving by 5/1000 of an inch at a time. Up, and over, and you need to be really careful not to crash, because you could crash this right into here. So I have enough practice at this point, but be very mindful of that. Bring it down till we're closer, and do a pretty similar thing to the shapeoko, where we're just going to line it up just so it's over. There we go. That looks right about over the edge. So that's aligning the x-axis going this way. So x is selected because we are last moving x, so we will touch off. And again, we are right over it, so we're going to hit 0. But let's say that we were in fact next to it, like we'd put our bit here, then we would put half the bit's thickness as the distance over. In this case, it would be negative because we're off to the negative side. Like that's our coordinate. But we're at 0. So we'll click 0, and now it moves. So now we're getting closer. Now we're in the right, but it's still clearly not quite right in the y-axis, because this is putting it like a foot up, and this is right down at the bottom. So now we'll do the y-axis by getting it lined up on here. Down here you can see that it's pretty darn good. So we can 0 that. Okay, and I'm just gonna, so you can see here that it says -14 because it's still thinking of its original placement of where it plopped it in there, but I'm gonna hit Shift hashtag, and what you can see is the Y is at 0.003 off the bottom of the y-axis. So it's pretty close to 0 on the y-axis. So that makes a little more sense. So now what we can do is on the y-axis, we're going to touch that off. Similarly, 0. All right, and now boom. So now this piece is exactly where we want it to be. I'm going to get rid of all the crazy yellow lines just by doing that, because we don't really care where we've been at this point. And so now it knows exactly where we are. So just one more note about the vacuum table, because we didn't talk a lot about that. The vacuum table works best for large flat things. It doesn't work for really small things or weird shapes, or if it's warped, or if it's very porous, then it isn't going to get a good grip on it. And if it's not getting a good grip, then you don't really need to use it. So this sheet of plywood is pretty flat, of decent size, so we'll use it. But if we were using something really small or a weird shape, then you don't need to waste the electricity and make all the noise if you're not using it. So for that, what we do is open the air channels underneath where your piece of material is. So the channels run the full length of the table. So in this case, these are, when they're horizontal, they're closed. So these are all closed. This is open, which is good because that's underneath where we are. as well as this one. So those are both open and this one's closed again. So that's good. In general, you don't want all of them to be closed when the fan is on, because then it's trying to suck against all these closed things. If you have all these bits and pieces on here or screw holes, then these stop the vacuum table from working very well because the material needs to sit very flat on here. So that's another good reason to clean up when you're done and when you're starting, make sure to vacuum the surface so your material sits really flat. And let's say you were doing a slab, like you had a slab of a tree that you were trying to flatten, then in general the vacuum probably is going to be very helpful for that. You'll have to clamp it down somehow. And in terms of touching off, you probably are going to, in VCarve, make just a pattern where it just is making a big pocket effectively, covering the whole area. And you'll say to take off 1/8 of an inch or something in a pass, and you'll touch off on your Z on the highest point, and your X and Y, wherever you put your XY datum, on the top surface. And then you do that pass, and then you just touch off your Z again. You can increment down so that you, with each pass, take off that material. And that you're probably going to be using this big 2-inch flattening bit. So make sure to use the appropriate feeds and speeds for that, because you can overheat the spindle and drive it too hard, and then you have to wait a few hours for it to cool down enough. So you want to make sure not to push it too hard. Another quick thought is that let's say you're doing a bunch of pieces that were set up on here. You had, say, 4 of the same pieces. Then potentially your Z offset could be the same for all of them if you're cutting through or they're all the same thickness. Your Y offset could be the same because they're all aligned on this line. So then each time you only need to change the X offset, which could be pretty nifty, that you don't need to necessarily retouch off every piece each time for all axes. Let's say that we weren't quite confident in our cut. We weren't sure that it was going to be in the right place. Something that you could do just to gain confidence would be to run your design a few inches up in the air just to see what would happen before running the final one. So the way you would do that would be by just saying page up until your Z, so right now the Z is at -8, call it, we would just bring it up to say -5, so it's higher in the air, and then you could touch off the Z, and then it would think, if we did that, that the material was higher up in the air, so it would do the cut up in the air, and then you could be comfortable that that's where it was. So when you're first getting used to the machine, I would definitely encourage you to do that to make sure that you are not going to hit something you don't want to hit. And now that the dust shoe is down, I can turn on this, which I'll do in a second because it's really loud, and the dust collector, which switches right on the other side. And then I'm going to hit the blue start button on the computer. If I see that something is going wrong, I'd hit P to pause it, and then S will resume it. And if it was going really badly, obviously I'll just hit the E stop to make sure it stops quickly, making sure that everyone's clear so no one's going to accidentally get hit by the machine. And if, let's say I wanted to go to the bathroom or something, if I hit stop, then I have to restart from the beginning of the program. So I could pause it, but the spindle will keep spinning when I click pause. So what you can do is go to spindle override in the corner and then just drop that slider down to 0. So that'll turn the spindle off. So then you can go to the bathroom, whatever, come back, bring the spindle back up to 100%, and then click S to resume the cut. You can also, let's say you think it's going too fast or too slow, you can modify the feed and speed using the override sliders right on the screen there, which is pretty useful. There are a whole bunch of other shortcuts on the sheet on the wall.
so it did our profile pass. In retrospect, it probably makes sense to do the engraving pass first before weakening the structure around it. So that's a good note for the future, is to do the engraving pass and then do your profile pass. But we're gonna come over here and load up our other programs. We're gonna open you, go to Pocket 1, and now we're going, this is just shown as where we did go, not where it's gonna go. So here we should be good to go, except now we did this one where it's referencing off the top of the material. So we need to make sure to reset our Z referenced off the top of the material. X and Y can stay the same. At some point in the future, we might have a way to touch off automatically. But until that point, we just have this technique. All right, so now that the piece is set back on the material, I went down 5/1000th of an inch. We're gonna touch off on the Z and say 0. Okay, and now we're going to turn the dust collection back on, put the dust chute back down. The reason this is adjustable is if you had different lengths of tools, you can set this dust chute to different heights depending on where you want it. All right, so the dust chute is down, the vacuum is on, and let's get it going. Ta-da! So we can shut this guy off, and this off. And I'm just gonna jog the head away so we can get to it. So I'm gonna put it in continuous mode so we can move it and do shift up. And now's a good time to look at this shortcut cheat sheet, because here you can just click C to go into continuous mode. There are a whole bunch of other useful shortcuts there. We can see our piece here. We could have used a down cut bit to make it a cleaner cut. So it didn't need to come up between each cut, so we could have modified that setting. But other than that, it looks pretty great. We just take a razor blade and cut through those tabs around the sides. It doesn't seem like it moved at all. It's still in there firmly, so it wasn't at risk of busting out when it was doing that engraving. And it obviously went much, much faster than the shapeoko could. So in terms of cleanup, you want to vacuum everything. You don't want to leave it dusty, dirty. Grab the vacuum, clean it all up. You can take if it's your personal tool in there, you can take it out, put the tool holder back on the rack, the collet in the collet holder. You can turn the air off and put the work holding clamps and whatnot back in the proper container. And if you have any difficulties or problems, obviously just post in Slack, talk to the facilitators, and I'm excited to see all the cool things that get made on this great machine. Thanks for watching.